We can go through the math and derive the equations. I'm sure none of you cares. So we'll just get to it and show you that kinetic energy is actually can be found by using this equation, 1/2 mv squared. That's how much kinetic energy an object has. So when a car is moving at 50 miles per hour, that car has a lot of energy in it. So that's why when they collide, the damage at 50 miles per hour is much bigger than if the car is moving 20 miles per hour. So if you have a car that's 2,000 kilogram, well, that's a heavy car, 1,000 kilogram, moving at a speed of 20 meters per second, or about 45 miles per hour, that car will have kinetic energy in it equals 1/2 the mass of the car, which is 1,000, times the velocity squared, which is what? 20 squared. And I think that's 200,000 joules. I think. That's a lot of energy. Now the same car moving at 10 miles per hour, miles per second, not miles per hour, 10 meters per second, not miles, 10 meters per second, about 22 miles per hour. The kinetic energy of the car is 1/2 the mass times the velocity squared. It has only 50,000 joules of energy. Notice when you double your speed, the amount of energy is what? 4 times. Not 2 times, 4 times. Why 4 times? Because when V becomes 2V, when you square the 2, what's the square of 2 is? 4. That's why at 10 meters per second, you get 50,000. Double that number. If you double the speed, your energy is what? 4 times that number. 4 times. Well, work is actually, definition of work is really change in energy. Which means if you have a car moving on a road, a flat road, I'm not putting any hills in it because that changes a little bit later, and you want to pass a truck, what do? You step on the gas and you increase the speed. So the car initially has a velocity of, let's say, 10 meters per second. You want to pass that truck, you step on the gas, now it's going 20 meters per second. That's your car. How much work was done by the engine of your car to get you from 10 meters per second to 20 meters per second? Again, the car has a mass of 1,000 kilogram. Work is change in energy. So that's the final kinetic energy minus the initial kinetic energy. Your final kinetic energy is 1/2 mass times final velocity squared, 1/2 mass times initial velocity squared. For this example, I have the numbers. I already got them from here. At 20 meters per second, your energy or kinetic energy is what? 200,000. At 10 meters per second, your kinetic energy is what? 50,000. So your engine had to supply 150,000 joules of energy. That's the work done by the engine of your car. So work is change in kinetic energy right now. Let's take another example. We have a 220 kilogram motorcycle. So that's the motorcycle with the person on top of it. And it's moving, cruising at what speed? Cruising at 14 meters per second. Doesn't seem fast. Again, times 2.24. That will tell you how fast. 14 times 2.24. About 31 miles per hour.
Where are you getting that 2.24? That's just too little.
Yes, the correction factor here,
Oh,
Alana.
sorry.
1 meters per second. Speed, where's speed? Speed. 1 mile per hour. 1 meter per second equals 2.24 miles per hour. And the question, what is the work, or what's the total work that must be done on the motorcycle to increase the speed to 19 meters per second? So how much work is required to increase the speed to 19 meters per second? Again, you're going 31 miles per hour, 19 times 2.24. You're going 31 to 43 roughly. From 30 to 40 miles per hour. Again, the work equals the change in kinetic energy. Change in kinetic energy is what? 1/2 mv final squared minus 1/2 mv initial squared. 1/2, the mass is what? 220. What's my final velocity? 19. 1/2, 220, initial velocity, which is what? 14 squared. And if we do the math, I'm getting rough 18,150 joules. That's how much work is required to increase the speed. So if you want to carry two significant digits, you'll say the work done is what? How much work? I need 18,000 joules. So that's kinetic energy. Again, kinetic energy, I'll put it here. It's 1/2 mv squared. Notice when I did the examples, both the motorcycle and the car, I made the assumption the car was on a flat road, not on an angle. Why? Because if there's a change in height, then we have to deal with what? Potential energy. So let's look at what potential energy is. What is potential energy? That's due to a change in height. Due to a change in height. So when you think about a box, you're moving a box upward. The box has a weight. That's your force. The weight, that's not work, that's weight. That's the force, equals mass times gravity. And if you move it up or down an h unit, then the work, I just write the word work because it gets confused with W, the weight, equals force times distance. Well, the force is mass times gravity, and the distance is height, and that's what potential energy is. This is the definition of potential energy. Now, some books will use U for potential energy. Not a mu, but the letter U. Looks like a mu here. I used to use P for potential. I think our book, the older edition, they use U for potential energy. Trying to peek at the book and see quickly what unit they use. Doesn't really say. I see an example. They write this, W mg, work due to gravity, mg. But I don't know if that's what they use for notation in this book. So let's take an example. If you have 4.1 kilogram book, so we have a 4 kilogram book, and you're going to lift it up vertically. Initial velocity was 0. The book was sitting on the ground. You're going to pick it up and move it a height. That's the 4 kilogram right here. You're going to move it a height of 1.6 meters. And we pushed it up with constant force. So we have a force pushing up constant. And the value of that force was 52.7 Newton. So constant force. So first question, what is the work? Done by the 52.7 Newton force. What is that work? How much work was done by that? 2. What's the work by gravity? Done by gravity. And 3, when the box reaches the top, what's the final speed? Find the final speed of the box. So these are the 3 things. Now let's look at the first one. The work done by the force, the 52.7. So the applied force, I'm going to call it the work. I'll put by the applied force, APP. That's the work done by the 52.7 Newton force. Work, we said it's force times distance times cosine theta. That's the equation we wrote early. Well, let's look at that force, the 52.7. It's pushing upward, and we move the box upward in the same direction. So what's the force equal to? 52.7. What's the distance in that direction? How far do we move the box in that direction? 1.6. And what was the angle between them? Between the two of them? Let's think again. 0. The force is pushing upward, the box is moving upward. They're both in the same direction. The angle is 0. So we do the math, and roughly that number is what? 84 joules? Give and take a little bit. Now, what's the work done by gravity? Now, let's look at gravity. Gravity, again, any work done by anything is the force times the distance times cosine the angle. Gravity, what was the force of gravity? Isn't that the weight, which is 4, or mg, I'll just go mg for now, times the height, that's the distance traveled, times cosine, what's the angle? Remember, gravity is pushing which way? Down. And the box is moving which way? Up. The angle is what? 180. That would be what? Negative mass times gravity times height. Negative because you're moving opposite direction. That's a negative. The mass, which is 4. Gravity is what? 9.8. The height is 1.6. Somewhere it looks like around 64, 63. Oh, turn the calculator on. 63 roughly. That's negative 63 joules.
I can't see that. Thank you.
Yep. I have to look see if I'm recording or not. What was the other question?
What is the final speed of the ball?
Okay. So what is the total work done? Let's look at the total work. There's only 2 people causing the work. It's us picking the box up and gravity pulling down. So it's the applied force by us, APP, that's the force we applied. And you're going to add to it the gravity. You're going to subtract the 2 numbers, but since the gravity is negative, so it's going to be the 84 joules minus the 63 joules. One is pushing upward, one is pushing down. So the net result of the work done should be the difference between them. 84 minus 63, which is what? Is that 11 or 19? 21? Is that 21, I think? Is that 21? 21 joules. Now, because I'm losing to gravity, that means what? As I'm going up, well, there's net work at the top here. There's the total energy from here to there. It's not a 0. If it was a 0, when I reach the top, my velocity is going to be 0. So now, then what's the velocity? Well, the total now amount of energy equals what the change, let's just put that, the change in kinetic energy. Which is what? 1/2 the mass times the final velocity squared minus 1/2 times the mass times the initial velocity squared. 21 equals 1/2. Do we know what the mass? I give you a mass for that box. Is it 4 kilogram? Yes, 4 kilogram times the final velocity squared minus 1/2 times the 4 times the initial velocity squared. (21 equals 2 v final squared). 10.5 equals v final squared. Can we get v final? The square root of 10.5. .24. 3.2 is good enough. Meters per second. That's how fast the box was moving when you get to the top. I'll give you a similar one to this, just in case you missed it. It's not making sense, and I'll put a twist in it. Let's say you take in somebody in a stroller here. So let me draw a picture of a stroller with a baby in it. These are the wheels of the stroller. Oh, I didn't mean to do that. They're connected somehow here. And there's the baby sitting right here. The stroller has an arm like this, and you're pushing. That's you here. Oh, you gotta lift your arms up, so you're gonna be pushing on that stroller. These are your hands here. Tall person. And you're pushing up like this on the stroller. So you're pushing force. Doesn't look right, the picture. Let's say you're pushing this way. That's you, I don't know. I need to make the person about 10 feet taller. But that's the direction you're pushing. So you're pushing on the stroller down on that angle. I'm going to give you an angle in a second there. Let's assume the mass of the baby and the stroller. Let's take some numbers here. What are we going to use? The mass is 22.7 kilogram. We don't want to do a large number like we did before. And the pushing force is at 44 Newton. But it makes an angle here. That angle is 32-degree angle. So that's you pushing the stroller. What is the work? That's the first question. Work done by you. To remove the distance, to move the stroller, how far? 1.2 meters. So the stroller is going to move right here. So you move that distance of 1.2 meters. How much work is done by you to push the stroller on the ground, 1.2 meters on the ground, horizontally? Again, if the initial speed is equal to 1.4 meters per second, find the final speed. Again, let's assume no friction. Everyone got the story there? I can put it again. You're pushing a stroller. There's a baby in the stroller. The mass of the baby and the stroller is 22.7 kilogram. You're pushing down this direction. That's the push direction of 44 Newton. And the angle is 32-degree angle. And the question, how much work is done by you to move this stroller on the ground? You're going to move it on the ground 1.2 meters. Second part, if the initial velocity is 1.4 meters per second, can you find the final velocity, neglect friction? Which way did the stroller move? My picture to the right, right? I need to find what portion of that force in that direction. So the work done by me is equal to force times distance times cosine theta. The force is what? 44. The distance is what? 1.2 cosine 32 degrees. Oh, I know what you're going to say. Why didn't you use negative 32, right? Well, you could use negative 32. Watch this. What's cosine of 32? What's cosine of negative 32? Same exact number. So if you want to use negative 32 degrees or positive 32, doesn't make a difference. So if that makes you feel better because it's below the axis, I'll put negative 32. Times the 44 times the 1.2. It's almost 45. 44.78. Is there any other forces acting on that beside me pushing that stroller? There's no friction, so I don't have to subtract any friction. Is there any other forces? No. So what's the total work? 45 joules. That's it. That's the only thing that's making the stroller move. I'm not putting any friction. Well, we know that's equal to the change in kinetic energy. 1/2 mass V final squared minus 1/2 mass V initial squared. Let's plug in the numbers. 45 equals 1/2 times 27, or 22.7, not 27, times final velocity, which I'm looking for it, minus 1/2, 22.7 initial velocity squared. Initial velocity was 1.4. 0.5 times 22.7 times 1.4 squared. That number here at the end is negative 22. When you bring it to this side, it becomes what? Plus 22. So if I take this one to this side, I'm going to add 22 to this, and that'll be what? 67. $11.35 here. $67 divided by 11.35, 5.9. And what's V final? The square root of that number. 2.43. And that's really what kinetic energy is, 1/2 mv squared.